Today I'm going to teach about the kinetic molecular theory, or KMT for short. So sometimes you'll see it, KMT. So far, right, we've taught you about all these gas laws, right? You got Boyle's law, right, that pressure and volume are indirectly proportional to each other. You got volume and temperature being directly proportional to each other, so that's Charles' law. You have Gay-Lussac's law, it says that pressure and temperature are also directly proportional to each other. And then you have the combined gas law, right, which takes them and puts them all together. Now, the thing is, in order to have these laws, we have to make certain assumptions about gases that are true in the right situations in order for these laws to exist. And for one more, called the ideal gas law. And so the ideal gas law requires something called kinetic molecular theory. So here are the postulates, or the things that correspond to kinetic molecular theory. Now, in your packet, you are going to find a page that looks like this. It says Kinetic Molecular Theory worksheet at the very top. And you're going to go through with me right now as we give you, so the first question says name the postulates, etc. We're going to go through them right now. So number one says, name the postulates of the kinetic molecular theory and state whether or not you believe they do a good job describing how a real gas behaves. So the number one kinetic molecular theory thing is that gases are in constant random motion. So gases are in constant random motion, meaning they're moving around a whole lot. This is very true. I always tell my students that, you know, if you were looking at gas particles and you wanted some type of like analogy to them, I always tell my students, you know, think like you had, you know, 30 5-year-olds in the room and you gave them all, you know, 3 candy bars each. Right? They would be moving all over the place. They'd be bumping into each other, be bouncing off the walls, right? I mean, there would just be constant random motion. And that's very true, and it's true of all gases. So that one I would argue is very, very true of how real gases are. Number two, the kinetic energy. Now, kinetic energy is the energy of motion. So the kinetic energy of a gas, is proportional to temperature. What does that mean? It means this. Now I'll write this up here. To temperature. So I'll put in parentheses, right? If you increase the temperature, you increase the KE, or the kinetic energy. Well, that just kind of makes sense in nature, right? Like if we took, you know, you and put you're standing on a bed of hot coals, and we took the bed of hot coals and we lit it on fire, right? So that the temperature underneath your feet was getting a lot hotter. I would argue that we would begin to move, right? Well, the same thing happens here with gases. As you raise the temperature, they begin to move around a lot more. Likewise, if you decrease the temperature, they stop moving. And that makes sense too when you think about that whole idea of, you know, absolute zero being 0 Kelvin or negative 273.15 degrees Celsius. So is this a good postulate? Yes, it is. Number three. Number three says gases have infinitely small volumes. So they have very small volume. Now, the reason that that's important to us is because technically they do take up some amount of space. But if you said, you know, your cylinder is 200, milliliters was the volume inside of it, I mean, technically those little gas particles in here would take up a little bit of that 200 milliliters. So really, when you go to do like a problem, like, you know, PV equals, you know, P1, V1 equals P2, V2, if I said this cylinder was 200, you know, milliliters, well, the problem with that is it's really not, for that gas, 200 milliliters, it's really probably like, you know, 199 and change, because the gases do take up a little bit of volume. But here's the thing, it's so small that we can neglect it. So gases have small volumes, so small that we can neglect it when we do calculations. And boy, that's important to us. It's not how real gases are in real life. But we have to be able to do that in order to be able to use the laws that we have, okay? Namely Boyle's law and Charles' law. Number 4, they don't interact with each other. I.e., they don't react with one another. Okay? Now, this one's kind of a weird one though, because gas particles don't interact with each other. Well, this one and number 5 are going to be almost oxymorons to each other, and the reason is this. Rule number 5 says this. If, actually, we won't even call it if. We'll say pressure is caused by the collision of gas particles. Well, the hard part about that is, okay, they're not going to interact with each other, but if they do, we're going to call it pressure by the collision of gas particles. So you can see how these two are really kind of not in opposition of each other. But again, we need these to not interact with each other so that we can think of them as separate entities within a particular cylinder, within a certain piston, whatever our container is, a vacuum, etc. So pressure is caused by the collision of these. I mean, obviously we see that when we do, hydraulic presses, right? If you take your car into the shop, they put it up on a hydraulic press and they use the pressure of water vapor, and gases in order to, lift your car off the ground. So this is a significant amount of pressure we can build using the kinetic molecular theory. And these 5 things have to be true in order for it to occur. Okay? Question number 2 on your sheet says, based on the postulates of the kinetic molecular theory, give the conditions of pressure and temperature you believe would cause a real gas to simulate an ideal gas. And the answer is if you had really, really high temperatures and really, really low pressures. So high temperature, low pressure. And number 3 says, Avogadro's law states that the volume of a gas is directly proportional to the number of moles of gas, but has nothing to do with the identity of the gas. Is this law correct for an ideal gas? And it's correct, or explained. And the answer is yes. And the reason for that is because in ideal gas, the molecules, they have no volume, right? Right here, number 3. So what happens is the size of them is negligible. And because the size of them is negligible, they don't interact with each other. And therefore, as a result, they behave according to Avogadro's law. Really, really a lot of words, but basically, long answer here is yes, Avogadro's law still applies to gas laws. What is Avogadro's law? 6.02 times 10 to the 23rd gas particles in a mole.